Hi guys, it's Rob from Royal Balls. I want to talk a little bit today about allelic combinations, what they are, how they work. I do have a vanilla scream clown clutch in the incubator, and my cinnamon Mojave paired to a black pastel banana clutch is due in the next day or so. Cinnamon and black pastel is also an allelic combination, so I do have some experience with allelic combinations. I think most people realise that with allelic combinations they act like super, so when you breed them 50% of the offspring will be one gene and 50% will be the other gene, and you can't get any normals. That's one advantage of allelic combinations. Another advantage of allelic combinations is, for instance, the vanilla cream that I'm hoping to produce in clown form this season. The vanilla and fire combination produces a combined effect which is a little bit different to what you would expect and produces quite a spectacular snake. Allelic combinations are often very different and much better than you expect them to be. The highway and freeway complexes, for instance, are spectacular examples of allelic combos where the resulting combination of the two genes is way different to what you would expect from the individual genes by themselves. But have we ever stopped to think about what the limitations of allelic combinations are? Those are the good things, but allelic combinations are difficult to work with because some combinations of genes within the same allelic complex are impossible. I have cinnamon Enchi in my collection, and have you ever thought, for instance, that super cinnamon Enchi and super Enchi cinnamon are actually impossible combinations? You cannot pair two snakes that will make that combination of genes, and there's only room for two genes of that particular complex at the address in the genetic material. So it's been a while since I've done one of my Professor Ball's pipe cleaner videos. For those that haven't seen them before, I have done a whole series of them before, but today we're going to look at the limitations of allelic combinations, why certain combinations in allelic complexes are actually impossible combinations. We're going to look at cinnamon Enchi and explain why super cinnamon Enchi and super Enchi cinnamon are impossible combinations. And then we're going to look at a project which is near and dear to my heart, the vanilla cream, which is vanilla fire. And we're going to look at Disco Inferno is disco fire, and all of these genes are actually part of the same allelic complex. And we're going to look at why a vanilla cream Disco Inferno is an impossible combination, why vanilla cream disco is an impossible combination, and what other combinations within that complex are also physically impossible to make. So let's get after it. Okay guys, I'm going to use the black background because it just gives the camera something to focus on. Now before you start running for cover, this is nowhere near as complicated as it's made out to be. For those of you that have seen my previous genetic videos, you'll know this is fairly easy to follow through. For those of you that haven't, just bear with me for a couple of minutes and you will see how easy this is. So here we have two snakes, male, female, and the genetic material is in a DNA double helix strand. So we have two strands of DNA in the male and two strands of DNA in the female, and this DNA contains all the material necessary to create a snake. It contains the code for the whole animal, not just for the colour and pattern mutations that we work with, which are actually genetic modifiers or genes, but this is the whole thing, the whole animal. And in sexual reproduction, just as in humans, father provides half of the genetic material required for the new snake in his sperm, and the female provides half of the genetic material required for the new snake in her eggs. And when we recombine them, we have all the genetic material required to create a new snake which is 50% dad and 50% mum. Hopefully the best qualities of both, but that's not always the case. But because there are only 2 snakes involved and each of them has 2 halves, there are only 4 possible outcomes in the offspring. And this is where the Punnet's square comes in. So we're going to talk about allelic combinations and why certain combinations are impossible. Allelic combinations act like supers, and by supers we mean the homozygous form of any particular gene. And I'm going to keep this simple. Let's use pastel, and I'm going to represent pastel by a blue paper clip. Pastel is a genetic modifier that attaches itself to the DNA of the animal carrying that gene, and that genetic modifier has a key or a code that allows it to attach itself only to that specific location on the genetic code. It's a unique code that allows that gene to attach itself. Because each animal has a double helix, there is room for 2 copies of the gene at that address, and this is where we get the homozygous or super form of that genetic modifier. So in this case we're going to take a male who is super pastel. He is carrying 2 copies of the gene at that address, and we're going to breed him to a normal female that is not carrying any copies of the gene. So here we go. The male generates sperm, so he splits his genetic material in half. Remember, the sperm only carries half of the genetic code, and that's going to combine with the eggs that the female produces, which also provide half of the genetic code. And in this case, because the male is a super form, he is carrying the genetic modifier on each half of his genetic code, so it does not matter which half of the genetic material gets passed on, it is sure to be carrying a copy of the pastel gene. So let's work out what the outcomes could be. We pair this half of the male to this half of the female, which gives us 1 copy combined in the new offspring, or we combine the same half of the male to the other half of the possible genetic material that the female could provide, and that also gives us 1 copy in the combined genetic material of the offspring. Likewise, if we take the other half of the male, again it doesn't matter whether we pair to this half or to this half of the female, the outcome is the same. So of the 4 possible outcomes from pairing a super pastel to a normal female, every single offspring will carry 1 copy of the pastel gene. It isn't possible to get a normal because the male passes on a copy of the pastel gene regardless, and the male cannot reproduce himself. It's impossible to get the super form because the male genetic material is split in half and he's only providing half. In order to get the super form of pastel, the gene must be present in both parents, and that's the same principle for recessive genes, where you need 2 copies of the gene to get a visual expression. Both parents must carry at least 1 copy of that gene in order to produce a visual recessive. So in this case, acts like super means that one of the parents is carrying a copy of the gene on each side of that allele. He is or she is homozygous for that genetic modifier, and all the offspring will receive 1 copy of that gene. What does that mean for an allelic combination? I'm going to use cinnamon Enchi as an allelic combination to show you what acts like a super means. This is a female cinnamon Enchi that I produced about 9 months ago. She is staying back, and the thing about this girl here is that not only is her pattern and colour rather unusual because of the allelic relationship between cinnamon and Enchi, but it also means that all her offspring will be either cinnamon or Enchi, not both, and you will get no normals from this girl, and I'll explain how that happens in a moment. let's take a look at another snake that also has this cinnamon Enchi allelic combination in it. This is banana cinnamon Enchi. It's a clutch mate from the female that we just looked at, and because this is banana, it's male. The non-bananas are female. We've also explained that in a previous video. But this is also cinnamon Enchi. You can see the expression of cinnamon in the bright orange of the animal. You can see Enchi in the banding, and you can see that the animal also has an extremely bright dorsal. So the interaction of cinnamon and Enchi is slightly different to what you would expect, but again, because this is an allelic combination, all of the offspring from this guy will be 50% will be cinnamon and 50% will be Enchi. He cannot pass on cinnamon Enchi in combination, and he also cannot produce any normals. So let's explain how and why that happens. So let's get out our Punnett square again and have a look at this combination. This is the female cinnamon Enchi that we've just looked at, and this is a male who is a normal. And the thing about allelic combinations is that just as with any other genetic modifier, they all have a key to one specific location on the genetic code. It's just that in this particular case, cinnamon and Enchi have the same key. So here we have cinnamon and Enchi on each side of that address, and again, when we pair the animal, the genetic material is split in half. So the reason that it acts like a super is that it doesn't matter which half you pick, there is a genetic modifier on each side of that address. It's just that in this case it's actually a different gene. So when we pair cinnamon Enchi to a normal, this half of the female, which is carrying the cinnamon gene, and pair it to this half of the male, so we get one copy from the female, no copies from the male. Or we pair to this half, one copy of cinnamon, no copies from the male. We take the other half of the female, it is carrying the Enchi gene on this half, we pair it to this half of the male, so we get one copy of Enchi, none from the male. This half to this half, and we get one copy of Enchi, none from the male. So you will see that every square, just as in the case of the super, every square is occupied by a gene. It's impossible to get a normal, but in this case 50% of the babies are cinnamon and 50% of the babies are Enchi. Notice that you cannot reproduce cinnamon Enchi from the single parent because of the allelic or acts like a super relationship. So 50% cinnamon, 50% Enchi. What does that mean in terms of impossible combinations? Well, if we wanted, for instance, to make a super cinnamon Enchi or a super Enchi cinnamon, is that possible? Let's see if we can make a super cinnamon Enchi. We know that in order to get super cinnamon, we need to have cinnamon on in both parents, so let's remove this outcome. And we're going to give Dad a cinnamon gene, but we're also going to give Dad an Enchi gene, just to make it even more interesting, because we can actually deal with super Enchi cinnamon and super cinnamon Enchi at the same time. Here's Dad, cinnamon Enchi. We split his genetic material in half, so half of the genetic material is carrying the Enchi gene, half is carrying the cinnamon gene. We split Mum in half. She is going to provide half the genetic material to the offspring as well. One half is carrying cinnamon, one half is carrying Enchi. So let's see what we get. We take this half of the male and pair to this half of the female, and we get 2 copies of cinnamon, super cinnamon. We take the same half of the male with the cinnamon gene and pair it to the other half of the female, and this time we get cinnamon Enchi. Let's take this half of the male and pair to this half of the female, and we get cinnamon Enchi. And we pair this half of the male to this half of the female, and we get super Enchi. We didn't get the combination that we wanted. We have one super cinnamon, we have one super Enchi, we have cinnamon Enchi and cinnamon Enchi. We do not have a super Enchi cinnamon or a super cinnamon Enchi. That is impossible. It's impossible to pair this combination of snakes and get the super form with one of the other genes. There simply isn't room on the allele for more than 2 copies, and when we split the genetic material in half, each of the offspring receives a copy of one gene or the other. It cannot receive both copies. Okay, so cinnamon Enchi, it is impossible to get super cinnamon Enchi. It is impossible to get super Enchi cinnamon. Any of the other allelic combos work the same way. It's impossible to get super asphalt yellow belly, which is the freeway complex. It's impossible to get super gravel yellow belly or super yellow belly gravel, which is the highway complex. Vanilla cream is the same. Disco Inferno is the same. All the allelic combinations work in exactly the same way. You will not get the super form with the additional gene. Okay, we're going to go on to something a little bit more complicated. We're going to look at vanilla cream, which is vanilla and fire, an allelic combination. And we're going to look at Disco Inferno, which is disco and fire combined. And you will see why you cannot get a Disco Inferno vanilla cream combination. It is actually impossible. So we're going to use blue for vanilla, and we're going to make Dad a vanilla cream. So vanilla, we'll use red for fire, vanilla fire. So Dad is a vanilla cream, and we're going to make Mum a Disco Inferno. So we're going to use green for disco, and we're going to use again red for fire, Disco Inferno. And you'll notice that disco, fire, vanilla all occupy the same address. These are all part of the same complex, and they are all allelic. So disco and fire is an allelic combination. Vanilla and fire is an allelic combination, and disco and vanilla is also an allelic combination because they occupy the same address. So what happens when we breed a vanilla cream to a Disco Inferno? Split the genetic material in half on both parents. We pair this half of the male carrying the vanilla gene to this half of the female, and we get vanilla and fire, which is a vanilla cream. We pair this half of the male, which is carrying vanilla, to the half of the female that's carrying disco, and we get a vanilla disco. We pair this half of the male with the fire gene to this half of the female with the fire gene, and we get a super fire. And we pair this half of the male with the fire gene to this half of the female carrying the disco gene, and we get disco fire or a Disco Inferno. So again, because of the allelic relationship of all of these genes, they all occupy the same address, the outcome of that pairing does not give us a Disco Inferno vanilla cream. That is an impossible combination. The outcome from this pairing gives us a vanilla fire, which is vanilla cream, a vanilla disco, a super fire, and a disco fire, which is Disco Inferno. Working with allelic combinations, you must understand potential outcomes. We are discovering more and more allelic combinations. A recent one that I saw from Justin Kabelka is spot nose and chocolate. They are also allelic, which means that in combination they produce a snake way better than you think the outcome is going to be, but it also means the offspring are going to be 50% chocolate and 50% spot nose, and spot nose chocolate cannot reproduce itself in the offspring. You must have the gene present in both parents, and there's only room for 2 copies of that particular gene from that particular complex at that particular address. So you are limited in the combinations that you can produce when you work with allelic combos. Okay guys, allelic complexes, more and more of them are being discovered. You will notice when you go to genetic calculators on Morph Market or World of Ball Pythons that the calculators also take some time to catch up, and many of the allelic combos that are recently been discovered, spot nose and chocolate for instance, cinnamon and Enchi, it's taking a while for genetic calculators to catch up on the fact that these combos are actually allelic. It's taken breeders years to find out that some of the more common genes are actually allelic, and when you look back at some of the snakes that you've been producing over the years, you suddenly realise that what you've actually been identifying in some of your combinations are actually misidentifications, and the snakes are not what you originally thought they were. As I say, some combinations within the allelic complex are actually impossible, and many examples on Morph Market of snakes within an allelic complex that have been misidentified. They're not what they're supposed to be because of the allelic nature of the relationship, but it is becoming quite trendy. I do enjoy working with allelic complexes, and I think from the video you will see why it's important to understand not only the good side of allelic complexes but also some of the limitations of working with allelic complexes. So I hope you enjoyed that. I hope it made sense. I hope it didn't disappoint too many people or was too controversial. I know some people are very skeptical about some of the allelic combinations. Some of them are pretty well proven, some of them are fairly new. And it does call into question some of the previous identifications of offspring that we may have made in the past without realising the combination was allelic. Jump down in the comments if you wish to ask any questions or you wish to question or contradict some of the things that I said. But in the meantime, enjoy. Keep working those allelic combinations within the limitations of what's possible and what's not possible, because they are phenomenal combinations. Don't forget to share, like and subscribe, and we'll see you next time.